Okay, we are back from a break, and we didn't have a lot of luck addressing technical difficulties. There's an access point just over there, and it just bounces on and off. And anyway. So it is difficult for the audience, I suppose, but we will continue with day 5, second half. I couldn't, it's too bad nobody can watch. So now it's off because it's blue.
Yeah, it's off right now.
Okay, so I just want to see. Yeah, no, I don't get anything either, so.
I just got it again.
Yeah, now I'm up to 80.
Yeah, I have signal right now. We should.
Well, okay, yeah,
Yeah, we
sorry.
should.
Yeah, okay.
Start.
I have to, I just give a little stop for a minute with the dice, just to give a little flavor of some sort of modeling idea, because we can talk about this now with conditional probabilities and random variables and such. So I can imagine a probability distribution that is more or less uniform, continuous value distribution. And I'll call it 0 to 1, doesn't matter. 0, 1. And I can take a sample from that distribution, and I'll start to plot a lot of samples, and I'll get a lot of dots that are distributed like the distribution. And so I have a picture of it that is distributed like that. Now, if I had if I was sampling somehow in, I don't even know how to do it. Well, forget the sampling. If I had data from wherever of 2 with 2 values, I had random variables x1 and x2. And I have a whole set of samples in these pairs. And I have values like 0.1 and 0.2 and 0.8 and 0.7. And x1, if I look just at x1 alone, and I plot a histogram, it looks like my uniform distribution. And the same is true if I look just at x2 and I plot it, it looks like the uniform distribution. But in this sample, we can clearly see, if you could read my writing, you can clearly see that here's x1 from 0 to 1, that we just plot against x2 from 0 to 1, and we plot x1 at 0.1 and x2 at 0.2, and we plot this x1 at 0.8 and x2 at 0.7. The whole thing looks like that, right? Or maybe it's not so skinny, maybe it's kind of all fat. But we'll say we like it nice and skinny. Well, we have a nice statistical model. We have like one of the probably most used sort of things in statistics and scientific research for that matter. And we say things about this like, if what's the probability of x2 being greater than an upper half, 0.5. What's the probability that x2 is in the upper half? This is a nothing fancy univariate probability of this uniform distribution, and half the values are in the upper half. All right. 50%. And let's see, how do I do this? Then what about, what is the probability of x2 being greater than 0.5 given x1 is some range. Well, okay, we can say x1 is greater than 0.5. We can just make it dumb and simple.
Damon, could we have the session shorter, like because of the technical problem? Could we do it until 6:30, I guess?
Yes. Yeah. We can talk about maybe. I won't propose anything online, so anyway, we can talk about if we want to do something. Okay. So now let's just think. Does this do anything for us? Is there some use of this conditional probability? If we, for example, if we knew something about x1, does it help us know more about x2? And the answer in this case is yes. Okay, so we want to x2, the probability that it's greater than 0.5. That happens up there. Is 50%. But now we're conditioning on within the context, or assuming we know x1 is greater than, as outcome in the greater than 0.5 space. So what's the x1 greater than 0.5? Happens up there. And so now we're looking at the probability of x2 being up here within the context that we know x1 is up there. So, I mean, we can do this as, well, we can't really, we need the correlation to do it right, but we can look at this just with a picture and judge it. Okay, we have, this is the part of x2 that's up there within the context of this space. And I think in this space, 100% of the x2 values are above that line. That's a much more certain thing, because we used the fact that these are very dependent in probability. This is the whole idea of probability models, is making use of this conditioning. We know something about this, and we're going to use conditional probability to say better things, more accurate things for here. And we could say, we could flip it here, say in the context, what is the probability of x2 being above the line, given that the x1, remember those are pairs, okay? We sampled pairs of things. Okay? Given that x1 is less than, well, down here. Okay, so we're in the context, we're in this context. Down there, what is the probability of getting a high value? And it is, it's this size divided by that size, or divided by the whole thing. We have just a little piece of that, and the rest of it is down there. That's off.
Yeah, I know, but this one is recorded.
And then, so this is useful. If you know things like if you know the weight of the person, it says something about the height. With varying accuracy. That you would hope to characterize statistically with probability statements. This is a case of strong linearly correlated random variables. We have two random variables that are not at all statistically independent. They move in a, not only are they statistically dependent interdependent. There's a conditional probability matters.
Damon, I'm sorry. Cesar says that we should end these in 15 minutes
Okay.
because of the problems we're having.
Yeah, I'm sure it's horrible for the audience.
Oh, just
Yeah, I'll just, that's fine. I mean, if say there's, otherwise I just do my job whether they watch or not. But we can do it again. So we will end in 15 minutes due to what are probably very annoying problems with the technology. Okay, where was I? Oh, so there is some sort of conditional probability connection with this, which we can mathematically do, but there's a very special nature of the conditional probability. It has a very distinct character to the way that the conditional, where the conditionality is. And that character is that it's linear. When x1 is high, x2 is high. Right? They follow in monotonic, and not only that, but the way I drew with a nice straight line. And when you have things like that, you can do much better than this. This is very crude. This is a crude model. We use x1 to predict x2 by splitting this space in half. This is a crude approach. But if we note that that's linear, then we can start doing things like saying, how do I write that nicely? Well, I mean, you just write the, you are essentially running conditional probability at the individual slices with a linear regression model. So here, I looked at conditional probability as a crude model to characterize x2 based on which side of the distribution x1 is. And I can do better than nothing. But if I look at the conditional probability of some fine slice here, I can say how do I do that? I just don't write the damn regression. x2 equals x1 plus or minus some error. That's it. That is the linear regression model. And so this is lets us characterize the x2 value conditioning on our x1 as a slice with some error. And so our equation is very good at saying we have the probability that, let's see, I gotta do this right. Let's see, I keep running probability distribution for x2 given x1 is about my slice area. And that probability distribution for x2 conditioning on this slice is a histogram that looks kind of like that. It's this spread here. I mean, that is simply, this is a true answer of a linear regression model where beta slope is 1, because that's what I said it was. The error term is not uniform in distribution, so that's a problem for. It's not a problem. But this model is the general form of a whole bunch of slow, painful slicing. So here's a slice, let me call this a R, something, slice R. No, I don't like that. Slice A. Okay, let's consider the probability of x2 equaling something, we don't know what it is, equaling something, we want the distribution. So, the distribution of x2 across different possibilities, given x1 is in slice A, right? In some little chunk. And we can look at the picture and just figure it out from the picture. We can figure out that x2, these outcomes, up and down, within the context of this conditional probability space, in the context of this little slice, we got 0 probability up here, we got 0 probability down there, and we have sort of uniformish probability from about this middle point spread out by plus or minus, I don't know, 0.25. So we could write down a function a little better than this. We could write something like f2 given 1 of x, distribution function for the second random variable, conditioning on the first random variable. You don't need to know this notation, don't worry. something like uniformly. All right, I got to take this and draw a picture, right? Take this. Figure that out. This is A chunk, so that's A. I like the little ones. This is about a third. Okay, so I got some value A in the middle of my little A's in the middle. A's right there. It's in the middle. My picture's not good though. Relax on my picture. Okay. So my probability distribution, x2 conditioning on the first random variable. I have to say what the hell I'm conditioning to. I'm conditioning to this thing, to this. This one being about A. A wedge is this function. 0, A, the slope is 1, A gives A. And what did I say, a third plus or minus 6. So I have A, and I have a third, and my distribution is kind of, I just miss a little bit, not perfectly squarish. Okay, so this is my probability distribution for this random variable conditioning on this area that's known. Now I can do this for a bunch of slices and draw a lot of pictures, or F2, 1 given 1 as A of X equals 0 for X less than A minus 1/6. That's it. It's 0 there. And it's 0 for X greater than A plus 1/6. And it's a linear function for a little short chunk here and a little short chunk here. No one cares about that. And so we just call it square. And so from if X is within the interval, open or closed, doesn't matter. Unless you're all into picky stuff. What the hell is it? Oh. A minus 1/6 up to A plus 1/6. On this interval, I call it uniform. With, so what does that make it? The value. What's this? For this uniform, continuous, random variable on an interval, the probability has to add up to 1. So it's tall. Okay? It's skinny. It's got to be 3 units tall because it's a third. Its width. It's A minus 1/6 plus its width is 1/3. So the thing, what the hell am I saying? 1/3 times 3 is 1. Oh, that's okay, I guess. Alright, well, I will not dwell on my stupidity. Takes on value of 3 on this short interval. Why am I confused? 3. Oh, because it's short enough. Okay. Forget it. I'm confusing myself. Okay. So you could write down the function if you care to. Picture works better. And this thing, you can do this a bunch of places, or you can think, oh, well, our error, this thing is kind of this 1/6 part, right? It's more or less A plus or minus 1/6. At least it is here. And if we do the same kind of chunk here, narrow chunk, we get the same thing. You just have to draw the picture better. And so we have some nice, we say, yeah, forget about that. We write down a probability model that says that we model x2 as the x1 value plus some unknown error, E, and this, we need to characterize this in a probability sense. This is,
Yeah, just conclude.
I finally get to talk and do something less boring. So what we've got here is this is the equation of a line that doesn't represent anything of actual data. It goes through it, but it's not based on individual data points. It's the idea. But this, when we let an error term in there, then we can actually start characterizing this stuff better. And we can say, well, we know that this is the shape of this random error part. This is not correct for least squares regression, where you should have a Gaussian error, but it doesn't matter. We can still do probability models with this, and so we need to characterize it as epsilon is distributed as uniform distribution centered at 0 from -1/6 to 1/6. That's the this is a way to write the distribution that looks like -1/6, 1/6, 3, and we now have a nice proper probability model characterizing x2 in terms of the x1 value and some defined probability distribution of error. And we can't do any better than that. So I guess I am gonna stop. Not yet. Because I would like to get. Oh, sorry. Damn it. This is a joint probability distribution of two random variables. Wow. There are two random variables. I don't want to split just yet. I want to just make sure. Okay. So, please consider the rolling a die and the outcome, which I called C and D. This is the lower half, 1, 2, 3, and the event outcome of odd, and figure out the, what is the intersection, what is of the two events. This is 1, 2, 3 for the single row. Anything in here, and this is 1, 3, 5. They're each one half. They overlap. They have an intersection. Play with that. And let's see, mutually exclusive. Yeah, I guess that. Shoot. Look at anything that, find a picture on the internet. Look for some two dice. When you search that, you will undoubtedly find some sort of Wikipedia page that has a distribution of the sum of two dice when you add up the numbers. And it looks like that. And this is a beautiful pachinko machine kind of example of the central limit theorem as it just starts to work. From taking a uniform distribution, 1 through 6, discrete but still works, and another one, and adding them up, and you get something that looks like this. And if you added up a whole bunch of them, you would get something that looks like that. Okay, I stopped. Thank you. End of seminar day 5.